is the Mach-Zehnder interferometer. I don't believe this is a Mach-Zehnder interferometer. This is a Buccini MIC1, but it functions similarly. So quickly I'll just go over how this works. There's a laser, Heaney laser here. It's 632 nanometers, so it's red. There's two mirrors here, and then it enters a beam expander, which increases the beam size and then collimates it so that it stays at a fixed size, sort of at any distance. Not indefinitely, but for the lab it's pretty good. Here up front there's a beam splitter. So what that does is part of the beam will go and get reflected to the left, part of the beam goes right, and then the rest goes straight. The left reflected beam hits this mirror, then this mirror, and you can change the path length of this by sliding it in and out. And this mirror is fixed. And basically by doing this and getting it just perfectly aligned, you can see an interference fringe pattern that the beam makes, and you can kind of tune it and kind of stretch the fringes out, move them around. And so that's basically how an interferometer works. You see if I totally tune it out of the way, you can see both beams, one on top of one below. So you can use this for gas measurements, things like that, all sorts of very sensitive measurements.
How happens to change the Mach distance?
So it doesn't seem to work too well with this one. I think I'm missing a component. But it should affect the quality of the fringes, typically. But I notice you really can tune it a lot better just by adjusting the mirror's tilt slightly. If that's hard to see, I've also got a beam profiler here, which we can slide into the path. So what this thing does is it has a rotating sort of slit in both the X and Y direction, and you can use this to sort of see what the beam shape looks like. The beam is a little bit larger than the aperture, so the Gaussian doesn't look perfect, but it does have, you can see sort of the top of the Gaussian, but the sides get clipped off. And we see as we adjust the, you can see the fringes here show up as you tune this in one dimension, and then you can switch it to the other. So I'm aligning this perfectly. It's hard to see both what the beam's doing. So there's some, so yeah, you can switch it from Y to X. You could do both, and you can see nice fringes with that. So it's not just an optical illusion, it's actually producing those fringes with the beam. So that's the interferometer. Part of the assignment is to draw how this works. You can either draw the Mach-Zehnder if that's all you can find online, or you can draw the diagram for this one. Any interferometer will do. And then you need to find some uses of an interferometer and just give a short list of that. Next what we're going to do is do a beam profile measurement. So this sort of shows you one beam profile of Gaussian. It's Gaussian in X, but it's got Y, it's got the fringes. Again, the beam is larger than the aperture on this. So to do what we're going to do is we're going to use this other power meter and then sweep it through one dimension of the beam, and then find where sort of the peak power is, and then you can plot each position and each power, and you'll get a nice Gaussian shape, or at least sort of Gaussian shape. So that's up to you guys. I'll get it set up for you. Let me save this graph here so you have something to compare to. So let me do that. And I'll send all this data to everyone. Okay, so that's that. So next to this one is power meter. So what we're going to do with this one, set it up sort of in the middle. It's a line. So that software is this guy over here. This is just a power meter. It doesn't show the profile, it just tells you the exact power. It's tuned to the wavelength. And there's a little Z stage here that you'll twist. And you can see as the beam leaves the center of the sensor, the power begins to drop. And we're just going to kind of do this to show that Gaussian profile. So if someone wants to twist the Z, and someone wants to read the power, and someone wants to write everything down, we'll get it done faster probably. So I'm going to start it in the middle. So someone needs to read off, the guy twisting this needs to read off the position. So it's a group effort here.
Do it.
Does anyone have questions about this? What we're doing exactly? So it's passing in one dimension through the Gaussian profile, and as you twist it, you know, when it's the full beam is inside the sensor, it's going to have the highest power. And then as you get away from that, it's going to drop. So use this to plot the Gaussian profile.
So 31 positions, really?
We don't have to do all of them. You can
Okay.
kind of jump by 10. Let's see. I think if you go to 0 and 10 on that Z, you'll be out of the beam. So maybe just do 10 positions or
Okay.
or 20, whatever.
All right, cool.
It says in steps of 0.125.
Let's do 0.5. Or wait, no, wait, hold on. So that's 1 inch total. So each of those increments is 0.1 inch. That should be fine enough. The beam's pretty large. I think when I first wrote this, the beam was tiny. So let's just do a 0.1.
Okay.
Maybe jobs can get switched out halfway through or something. Does that work?
Sure. All right, so it's 377 microwatts.
What's the position?
0. I guess you're
So I
supposed
think
to.
it's starting at 0.5. So it's in the center. Here, maybe I should. Let me just start us at all the way at 0, and we'll go up. That way it's simple. Hopefully this thing doesn't tilt, but it's not exactly fixed. Alright, so there's 0. Obviously it's not going in. And then we'll just go up a little bit by a little bit.
So that's 0?
0 is showing up as 0.1. I think that's just the background line. But this thing's a little slow.
All right.
Takes a while to, I guess, integrate.
0 equals 0.
So every 4 turns will be 0.1. So it says
That's 0.6.
$2.15.
Does anyone want to relieve initiative? Maybe we'll wait for the next number.
I think they're done.
That's 0.7.
Maybe wait a second. So. And Nelson Grant. Just get back down to 0.
So
Or
175.
0.3, whatever the lowest was. I'll give it a go.
What, this thing?
Yeah.
Which way?
Where'd you fork?
Clockwise.
It's going up.
Yeah.
Clockwise.
Yeah, you got it.
This way. So 4 turns is 1.
Okay. Okay. That's 4. So it's on 0.8.
Why is it?
Huh?
Why does it increase?
Why is it increased?
They get twisted.
Yeah,
it's at
I
point
think
eight.
he went opposite. Did you went the opposite direction?
I went up to point eight.
And it went up.
Yeah,
That's not good.
it's at point eight now.
You know what? I might be doing the interference fringe thing.
Well, people can
Check that.
extrapolate
Yeah.
if they want.
Right. Sheet. Don't quite have a fixed thing for this. But anyway, it's described with a transmission-based diffraction grating. And unfortunately, the only one we have is pretty crappy. So it's just like a thin, translucent piece of card. But if you use this for reflection, diffraction. Shoot. Got too much crap here now. Yeah, you can't see many. You won't be able to. There. Okay. So you can see only really the first order diffraction. Maybe someone could turn the lights off. Right there. So you can only really see the first order on the sides. This one doesn't give a second order, so it doesn't really work well for this this lab demo. But you'll notice as the distance changes, the distance of the first order diffraction peaks also changes. We do, however, have a reflective base diffraction grating, so this one's nice and shiny. The one thing that's nice about this one is that we can get all the orders. Let's see if I can figure out a way to sort of, it's going to be hard to position. There isn't really a mount for this because we took it out of a piece of equipment. I'm not quite sure how we're going to do this. So we have to measure the distance between these orders. And I don't know if I can do that. I think I'm going to have to turn this so we can get a nice solid wall on this. So with this one, you can see that there's a first order, second order, and third order. And they're all there. So it's hard to figure out which one's which. Okay, there's all three.
Brightest will be the first
Yeah,
one.
there's all three there. It's a
Yeah.
little bit distorted, but you can see all three orders.
Why is it in one direction?
I'm holding it at a 45-degree angle to the beam.
Oh, okay.
Yeah. So currently my hand's like this, oriented. So it's roughly a 45-degree angle. But I think we should be able to measure the distance between these and figure out you can do the math to figure out, I forget exactly, yes, calculate the grading period. So this has a misty period. I'm sure if you looked up the part, you could figure it out, but if you do the math, you should be able to figure out the grading period of this based on the distance between these, each of these dots. So I'm going to quickly see if I can find a way to hold this in place, and then we can measure the distance.
We can this one. We can use
It might
this.
work.
No.
One thing I'm worried about is I think it's like directional.
Is it?
Yeah, so I need to keep it oriented a certain way. And it's going to be difficult.
Yeah. It's.
We're going to try it though. Let's see. Let me hold that in place with that.
Can you switch on the light?
Yeah, that might be helpful. Thank you. So nobody touch the grating if you can help it.
No.
What we're going to do is move this out. Hopefully the math still works out with this question. I don't have a way to mount it though, once I have it in there.
Oh God.
That's a good idea. Do you have to unscrew it, Roger? I don't know how that works. Am I breaking it?
No, no, you might break that. Wait, it's something like this. Oh, this way. Not this way.
But that just moves the whole thing over. if it's being used correctly, but I don't know how I'm gonna hold this either.
Oh god. Okay.
Come on. So we can just sort of plop it in there. We can use this thing. Sorry. Bit of a mess today.
Oh, that's.
I'll stretch it back later. It's gonna be too high.
Okay. It's too low. Oh god. Leave it. I mean, you can do it like manually. It's okay.
Well, we gotta get it fixed so that you can measure the distance from everything. So let's try that again. Sorry, that sounds horrible. Ah, there we go. Maybe we can balance it on that somehow. So, yeah, that might work. So I think what we're going to want to measure is the distance from the grating to the
Yeah, scale right. Wait.
wall. It might be a slightly different equation than the one in the lab because we're using the reflection. We can measure the transmission grating too as well. Grab a ruler real quick. Maybe everyone can kind of play with this for a second and see how this works. I'll go grab a ruler. Turn the lights on. Maybe more through one than this. Okay, I'm good. Close enough, I guess. Oh, it's pretty far.
Can you hold it? Just hold
So you can see how you.
Let me get a scale.
See if you can see all three. See if you can see all three of the
Like this.
Yeah.
diffraction orders.
But
there.
the first one is like half.
There is some distortion. I think based on our.
I can see the number.
Yeah, I got that.
Can you switch on the light? Just one light.
Yeah. Oh, it's really.
We need a better reflection, huh?
Approximate, just do
Yeah,
it.
yeah. Could you read the number? 6 to 5.5, I think.
So
You're measuring the last one.
Oh no, it's 5 point.
it's
5 point.
roughly like 2 millimeters and 8
Just
millimeters.
take the camera.
Or
angle from-
centimeters.
Yeah, 2 centimeters and 8 centimeters. That seems
Roughly.
right. Yeah.
You're gonna have some error with that, but it sort of shows you what's happening. Yeah, we can also we'll do the transmission grading and just show. You only see the first order, but you can use that to do the lab part. I think you only need one. The largest reflection is the zero order, so that's like actual
Right.
angular reflection. But then the rest of those are based on diffraction.
Done.
So the numbers you need are so laser wavelength. That's 6. So now that we have an easily fixed distance, we can easily see the first order. Zero order is obviously in the center. You get it on both sides because of the grading, but unfortunately this isn't really high quality, so you can't. The second order is really hard to make out, even if it's there. It's gonna be really hard for you to see with your natural, like with the human eye. Just keep that fixed. So now we can maybe get a little more accurate measurement. So this is transmission based, but you're not going to see the second order. It's the only issue. We can adjust this and you guys can measure it however you like it. Obviously change the distance from the back screen here. The distance away there will also change. Yeah, if you get it too close, you can't measure.
Yeah.
So maybe you should film.
Yeah.
Okay. So you have to measure that one. Maybe draw a line down the right side and write those down as well. Anyone else want to do that? Who hasn't done anything yet? Have you done anything yet?
Yes.
You did?
I'm already with my equipment.
I can try.
Okay. So you can, you can put it at any distance you want. You just need to measure the distance. Obviously, it's too close, I think, to measure right now. But
Yeah,
you see the first order, right?
You want it?
From
Wait.
here.
Taking a step. No. You can measure
The
it, I
distance
guess.
from the screen to the back wall. The diffraction grating to that back wall there. And then also the distance from that zero order to the first order.
From here to the back skin here.
Yeah. Right. So maybe you can
It's
make it
kind
just
of-
you can make it the entire distance of the ruler. Just to make it easy on yourself.
It's around 6 point. Is this 7? Oh, this is the opposite way. Okay, just a minute. From 6 to up. I have my.
Oh, there one. Here?
Yeah.
3.25 to 6, right? This
Or you
direction.
can go this direction. It's around 7.
Oh, this one.
Yeah.
So 7.
Yeah.
7
Hmm?
unit is
So
centimeter.
so we got the laser that we're using the
I think
transmission
this
grating
is-
now. So this is the distance screen.
Yeah, start.
So, yeah, sure, that might help. If you turn off the lights real quick. So I'm putting a linear polarizer in the beam back here. And we're going to just see how the reflection changes as we rotate this. So it's going to be really difficult to see. But for this orientation, it doesn't seem to change much. Sort of the refraction or this grating. You can see the polarizer actually. That's pretty cool. I don't know if anyone can see that. Those are the lines in the polarizer. But anyway. So, can you see through the paper?
Yeah.
So in this orientation, it doesn't seem to change much. But if we switch it this way, oh, there's already found it. So there's sort of the Bruce triangle. There's less light coming through this way. Already. That's really blocking it. That seems something to zoom right. I think it's already getting polarized.
Yeah, his.
What's that?
That's a reflection, I guess.
Right. But it's canceling everything out. It's a really broad Bruce triangle for this one. It's less intense the other day. That way you can still see it. That way nothing.
Wait.
I wonder if this is polarized already. Oops. That's not right. I need to remove the Heaney laser and flip it around, which is going to ruin the interferometer. Alright, let's try it with a different laser, but I have to go grab one real quick. That way it's a little more hands-on.
Yeah.
Normal to it. It's not really working. Who built this?
It's not me.
Okay. So that's a little brighter too. It doesn't blind anyone. I'm keeping it low, don't duck down, I guess. So we have
Hey. Oh god. Okay.
what is it?
Oh, paper. Okay, that's fine.
Just tape it on real quick. shape it one way.
I'm holding it. Give it. I'm holding it.
I can't hold it while we do a measurement. This isn't going great.
That's fine. Okay.
I can prep that on both sides. So we have it oriented one way. Doesn't seem like there's much of a change. But if we rotate it, we should be able to see the Bruce triangle. There we go. Does everyone see that?
No.
Yeah.
Right there is the Bruce
Right there,
triangle.
then,
For
yeah.
So this is TM, and if we rotate it, it's in TE. And you can see the TE glass is shifting. So at TE, it's pretty bright, and then TM, you should see nothing.
Because
least
it's
it's right
hitting the metal thing, so that's why it's reflecting.
Oh, is that way, one way? Okay, but anyway, there's still a local minimum you can see
Yeah.
there that's not present in TE. The challenge now is measuring
Power.
the power
Yeah.
for 10 angles, both TE and TM. One issue with this is that, you know, as you rotate this, the reflected beam is going to change a lot, and there's no real good way to keep it in place. So it's going to be a little bit, it's going to be, I guess, a bit of error in this measurement, because this meter doesn't work well. How can I do this?
Take
Move
this
the
thing
fi-
away and we can try.
I need a stand for this, and then we'll just do this meter. So while I get a stand for this, so fuck, this thing's annoying. Take that one out. And take this one out. Alright, so I'll get us a stand for this. Everyone else can play with the.
There are angle markings on that rotating thing.
So you guys can play with the. Yeah, there's angles on the stand there, so you can see the angle.
Yeah.
They're not quite. Zero isn't set to zero, so
That's the minimum, I guess.
First, take the
I think.
see the angle first,
Oh, yeah.
like the perpendicular angle.
Oh,
First.
God.
Little bit
So
more.
this is 90, I guess.
Little
Right.
bit more.
This way?
No, no,
Oh, different.
no.
Opposite.
It's like
This
yeah,
way?
yeah,
fully
yeah.
reflected back.
Yeah, so
Yeah.
this is 90, right?
How much
Yeah.
is the angle?
140?
140 is the starting angle.
Yeah.
Okay.
Write down 140, like the starting angle. And when you rotate, you just find the difference. That's your angle of incidence.
Yeah, now it's like 60. Yeah, 80, sorry. 81 or 82, something around that.
So,
So that's the minimum. It shows like the minimum thing.
so it's 60 degrees.
Yeah. Around 60.
I don't get it.
The angle, Brewster angle is around 60.
So no, the 140
Oh.
is where the light
started.
is going back.
Okay.
So it's like a reference angle. You're
Okay.
changing it.
be more than 90?
I'll talk to you afterwards.
Okay. Brewster is around 60.
okay, cool. Alright, so everyone get the chance to sort of see it. TE and TM. I'm glad you guys know which one is Brewster's angle, because I don't remember. Alright, so we're going to try this to sort of measure the reflection, the power. And we're just going to plot that for each of the things. So we can get the height right. So we're going to have to move the meter every single time, which is going to cause a lot of error with the powers, but
But it will hit, right? It will hit
Yeah.
the middle.
so somehow this is negative.
A little bit-
Something's wrong with this meter.
Should it be a little bit more higher?